Okay, we will continue our lectures. This morning we were looking at introduction to shock waves. Basically, we looked at the normal shock, and we also looked into the oblique shock, and we looked at the ways how we could calculate use the normal shock tables for shock applications by dissolving into normal components, and we also tried to apply it on try to solve a few problems, and we applied it to one of the problem with the multiple shock train inlets. Inlets is a big ocean, but we'll see how much we could cover this afternoon, and we'll start. Now, when you look at the supersonic inlets, the function is very similar to that of the subsonic inlets. In subsonic inlets, we try to decelerate the flow to the phase to Mach 0.4 to 0.6. For gas turbine engines, basically the compressors are suitable to handle the flow of that range. But here we are looking at a very similar application to decelerate the flow so that we could have larger residence time in the combustor. So we looked at this supersonic inlets. We looked at this inlet in subsonic applications in the very first lecture. We looked at the inlet pressure recovery, and we also solved a problem where we saw that the inlet pressure recovery improves when we have more number of shock trains. So we have if you decelerate the flow over multiple shock trains, then the inlet pressure recovery improved. Yeah, now I need to just mention something about some terminologies which will be useful for supersonic inlets. So here you see this is the compression ramp, and here is this convergent and divergent one. Now here is the cowl. This is called the cowl inlet cowl lip. So now you can see this is the projected area. This is a projected area. So this is the actual geometrically projected area through which we can swallow the air into the engine. So theoretically, this is the A1 is the area through which we can swallow the air. But in reality, what actually happens is at higher Mach numbers, you have this green line. What you see there is the oblique shock that forms. Partially, it is required to decelerate the flow and to pressurize the air getting into the engine. Now, from the theory, what we have seen, when the flow encounters an oblique shock, the flow will turn. Now, due to this turning process, we can see that beyond this level, whatever the flow that turns is being lost. We are losing the mass. When we lose the mass, then probably you can see that it has an effect on the thrust that is produced by the engine. So this amount of the A1 minus A0 is basically defined as the spillage. Okay, so we have defined the term spillage now, which is important because we don't want to have excess spillage. If we lose mass, then eventually this will affect the thrust that is being produced. At the same time, we have seen this morning that we want to have a good inlet pressure recovery so that we are effectively ingesting the mass of air into the engine with reduced losses. So when we try to decelerate flow from supersonic to subsonic, it involves shock waves. When we talk about supersonic inlets, they're dominated by shocks. And when you talk about shocks, shock interacting reflection and shock boundary layer interactions are a bit crucial, very important for supersonic applications, especially with the inlets and nozzles. The shocks will induce instability, and we'll discuss about various approaches that can be used to stabilize them. Supersonic inlets are not isentropic because of the formation of shock waves. So you have to deal with the shock solutions. But nevertheless, we have to start with something which is much more simpler. So we are going to look at the isentropic inlet study to provide some physical understanding of the flow behavior, and then we extend it to shock applications. So this is what I thought we will look at it this afternoon. Start with the convergent divergent inlet, and then we will discuss about starting the inlet. I'll let you know what starting the inlet is. Then discuss about the normal shock inlets, external compression inlets, variable geometry, external compression inlets, and mixed compression inlets. So we're going to look at the convergent divergent inlet. So when you look at the convergent divergent inlet, so here you can see that this is a convergent divergent inlet. I'm sorry, because of this spreading, I think the whole thing has been shifted. Okay, so here I think what you see here, this is what we are looking at. So here you see the geometry, it is of convergent and divergent geometry. And this is the inlet, which is normally for, this is an F-35 engine aircraft, F-35 aircraft. So here you can see, look at the inlet here. So here you can see the inlet here. That is how it is. So you see this convergent divergent inlet. When we are very quickly, I just want mention something here. Let's look at this flow or geometry here. This is the mass flow rate. The mass flow rate is rho a v. Now we have seen that the properties are denoted in terms of total properties, where we have pt by p is equal to 1 plus gamma minus 1 by 2 m squared power gamma by gamma minus 1, and we have tt by t is equal to 1 plus gamma minus 1 by 2 m square, and then we have rho t by rho is equal to 1 plus gamma minus 1 by 2 m square power 1 by gamma minus 1. Now ideally, when you're looking at the mass flow rate, we want to express it in terms of total properties as well as in terms of Mach number. That's what we really would like to have. So a very quick way to do it is the mass flow rate per unit area is rho and Vt. So then if you want to express in total properties, V is equal to mc, and rho, from this equation I can write here, rho is equal to rho t by 1 plus gamma minus 1 by 2 m square power 1 by gamma minus 1. Okay, so you understand this one here. So I can express this as rho t divided by 1 plus, I can express this by power 1 by gamma minus 1. And then I have this Mach number here. And then C, I can write it as square root of gamma r and square root of t. C is equal to square root of gamma r t. So then from this expression on temperature, I can write here mass flow rate per unit area is rho t by, you know this term, box term is 1 plus gamma minus 1 by 2 m square, 1 by gamma minus 1, and here you have Mach number here, square root of gamma r, and then this I can write it as tt. How do I write it? Because this is the equation here. I can write this as tt. T is equal to tt by 1 plus gamma minus 1 by 2 m square. Is that clear? So I can write here the t as t, this is power, this is the term here, So for the sake of convenience, let me put this as x here. So 1 plus gamma minus 1 by 2 m square. I'm just putting it for x for the sake of speeding up the process here. So now you can see that the denominator terms, it is x power 1 by gamma minus 1 into x power 1 by 2. So it is basically 2 into gamma minus 1, 2 plus gamma minus 1. So this is basically x power gamma plus 1, 2 into gamma minus 1. Are you able to follow what I'm trying to do, all of you? Yeah. So we have rho t is pt by r dt. Clear? Rho t is written out here. And here it is em square root of gamma r. Okay. And then you have square root of t divided by 1 plus gamma minus 1 by 2 m square gamma plus 1 divided by 2 into gamma minus 1. All of you understood what I'm trying to do now? Yeah? This is t. So now I have 1 square root of gamma here in the numerator. 1 square root of gamma. Is that clear? Numerator. If I cancel off this 1 square root of r, I will have 1 square root of r in the denominator. If I cancel this square root of t, I have 1 square root of t in the denominator. Understood? Okay. So what is left out here? pt into m divided by 1 plus gamma minus 1 by 2 m square power gamma plus 1 divided by 2 into gamma minus 1. So this is the mass flow rate per unit area. If I call this as equation 1, then at critical condition, normally the critical condition is at the throat where m is equal to 1, then the equation 1 reduces to the form m dot by a star, which is equal to pt square root of gamma by r dt 1 divided by gamma plus 1 by 2 into power gamma plus 1 by 2 into gamma minus 1. Can you follow what I'm doing here? I'm just substituting m equal to 1 in the mass flow rate equation. When I do it, I get this equation 2. Okay, so the next step, I'm having equation 2 divided by equation 1, which is mass flow rate by A star divided by mass flow rate by A, which is A by A star. Dividing equation 2 by equation 1 gets me A by A star. So what is that one here? So here I have pt square root of gamma by rtt, and here it is 1 divided by gamma plus 1 by 2 the whole power gamma plus 1 by 2 into gamma minus 1, that's in the numerator, divided by this equation 1. The equation 1, I have pt square root of gamma by r dt em divided by 1 plus gamma minus 1 by 2 m square power gamma plus 1 2 into gamma minus 1. You see what I've done there? I have I have started with the basic continuity equation, mass flow rate. Yeah, let me wait. Okay, finished here. I was going through it quickly because I thought it was a superfluous information. So what I did was, this is a geometry I considered. That's a mass flow rate continuity equation. I wanted to express this mass flow rate in terms of total properties and in terms of Mach number. So these are the relationships, isentropic relationship between the local and stagnation properties. So I replace this with those properties. Then after rearranging it, I arrived at an expression for the mass flow rate. That is what you see here. Pt square root of gamma by RTT into m divided by 1 plus gamma minus 1 by 2 m square power gamma plus 1 by 2 into gamma minus 1. That's the mass flow rate equation. Now I try to apply it for the critical condition. Wherever m is there, I put 1. The equation reduces to this form. This is equation 2. Now I took equation 2 divided by equation 1. I get an expression a by a star. A by a star. So now I have written this equation. So now you can see that this entire term cancels off. So what is left out here? Now this term is in the denominator of the denominator. I can take it to the numerator. Okay. And this is also in the denominator of the denominator. I can take it to the numerator. Okay. So if you just observe what I'm writing here, a by a star is equal to 1 by m. This m, I've written it there. And then this term, I'm writing it as 2 divided by gamma plus 1. Okay. There is power there. I'm not writing the power. I'm just writing only the base term there. Then here I have this term. It's in the denominator of denominator. It goes to the numerator. It is 1 plus gamma minus 1 by 2 m square. So now you can see that these two bases have the same power, gamma plus 1, 2 into gamma minus 1. Understood, all of you, what I've done here? So I've expressed the mass flow rate in terms of total properties and applied the critical condition and taken the ratio of it. When I do it, I get the relationship a by a star. Now you can see that this a by a star is dependent only on the Mach number. Okay, so if you just write a small code or just vary the properties, gamma is fixed. So this is what you will get. When you vary the Mach number, a by a star will get a shape something like this. So here is this unique one, m equal to 1, which is a minimum 1. And here it is a subsonic solution, and here it is the supersonic solution. So one of the things what you need to know is that for a given supersonic Mach number, for let me say some supersonic Mach number here, let me call this is the design supersonic Mach number. I will have the provision, the ability to design A1 by A throat. So which means I can design the inlet dimensions like this. So here it is A1, A throat. I get it from this graph. This is from A1 by A star. Now, one of the things what you have to understand is, I'll go back to the, there are for a given geometry. So now you can see that I have defined the geometry by fixing the Mach number. for this Mach number, I can see that there is an unique subsonic solution, and there's a, even though I have designed this inlet to operate at supersonic speeds, it has a unique subsonic solutions, which makes it even more complex and difficult, because at this unique subsonic solution, the flow gets choked at the throat. At this condition, at subsonic flow, Mach number at the throat will be 1. It adds a lot of complexities. Okay, so that's what I'm going to discuss it now. So this is what okay, you're able to see that there, yeah? So now you understand this one. So aircraft, this is the aircraft inlet. If I want to design the inlet of this F-35 aircraft, if it's of, this is of convergent divergent geometry, then this isentropic solution plays a very important role, which says that for a design, I have chosen a design Mach number, so somewhere here. So I can use this one to find the A1 by A throat. So you identify the design, because when you design an aircraft, F-35 Raptor, it is designed to fly at certain Mach number. For that Mach number, what is the inlet configuration? So okay, the convergent inlet that is designed to fly at a design Mach number will experience choking at its throat before it reaches MD, because I said that it has a unique solution, subsonic solution. Okay. So if I choose this is the design, then I have a unique subsonic solution here. Even when the flow has not reached the design, the throat becomes choked at this subsonic condition. Are you able to understand this? This is the important thing you need to understand. Okay, now let's look at this one here. Now what I'm going to do is, I have now designed an inlet based on the design flight Mach number. In this case, I just chosen for a numerical value of 1.8. For M 1.8, if you look at the tables, where's the tables? You can say that I can, there is a by A star, 1.8, A by A star is 1.439, something like that. Okay, so I'm just giving an example here, numerical. So that is the A1 by A throat, A1 by A throat, 1.4, something like that, 439, yeah. Now what I'm going to do is to look at the sequence of events that happens when an aircraft, a supersonic aircraft, is to fly, but it is about to take off from the runway to accomplish its mission. Now, what are the sequence of events that take place when an aircraft starts from rest until it reaches the design conditions? So how are the external performance of the inlet and the internal performance of the inlet? Now, let's, so if I have to start from rest, I have to start somewhere here. This is Mach number minimum, this is going all, okay, I'm going to start all the way from rest. So I'm going to go all the way from here to here. If I have to go all the way from here, I have to start from somewhere here. So, and then march in this direction. That's what I have to do. So I have just chosen few station points. So one is what you see here. The engine is very thirsty. It wants more air. So this is the capture ratio. So A0 by A1 is what we call as the capture ratio. These are the imaginary streamlines which is depicting the flow flow lines, what you see there. It is greedy, it wants more air. The capture ratio, A naught by A1, A naught by A1. A naught is unperturbed free stream, A1 is the inlet lip of the aircraft. A naught by A1 is greater than 1. Okay, now we are trying to accelerate the aircraft. It has taken off from the ground. It is greedy, it wants more air. It is now propelling. And then you are accelerating it. We have come to this point here. You can see that capture ratio decreases here at this point. So you can also see this from the graph here. So we are at this particular point. The capture ratio decreases. Now at this point here at 1, here subsonic flight is designed to operate at supersonic. It has to go from subsonic. The inlet in the convergent part is subsonic and divergent part is also subsonic. Now as it accelerates, the capture ratio is still greater than 1, still subsonic flow, because this is the supersonic condition. This is the Mach M equal to 1 condition. We haven't reached even that critical condition. So still subsonic flight. M is less than 1 at the convergent part and M is less than 1 in the divergent part. Now what you see here, we have come to this station 3, where it's a unique subsonic solution of that particular inlet. Now we haven't reached the design. We haven't reached M equal to 1. It is still at subsonic. M equal to 1. Capture ratio is 1. A naught by A1 is 1. So Mach number and the convergent part is 1. Mach number at the throat is 1. The flow gets choked even under subsonic conditions, though it has been designed to fly at supersonic flight conditions. And then this is still subsonic flow there. Now we are going to still accelerate it. Now you can see that the capture ratio is less than 1. The capture ratio changes. The flow profile changes here. Now at this point, something interesting happens. The engine wants more air, but the throat is already choked. So the ramming effect is taking place. The more air is being pushed into it, more air is pushed into it, it is being choked. So you can see that the pressure, the green lines here, the pressure wave starts to build up. The pressure wave starts to build up as we try to accelerate it. So you can see that still it is subsonic in the convergent part. It is choked at the throat. The pressure waves are building up here. Still it hasn't reached M equal to 1. Now we have just come to the station 5, low supersonic regime. We have gone through this transonic regime. Now the aircraft is now gone into the supersonic regime. The pressure waves, they coalesce. Now one of the things is, we'll be looking at it, the pressure waves are very unstable in the converging part. So they are all being pushed up, they coalesce to form a weak shock wave in front of the inlet. Now you can see that, as I said this morning, you can see that there is some spillage of air that is taking place. Still it hasn't reached the design condition, because this inlet, this aircraft has to operate at MD, but it hasn't still, it's already struggling with losses happening here. It's losing some mass flow. Okay, so capture ratio is less than 1, and then it is a supersonic speed operation. Subsonic, a convergent part, throat is choked, and here it is subsonic. Now we have reached the design condition. Now when we reach the design condition, we end up in a very strong bow-like shock that is formed on the outside of the inlet, which is not a desirable condition. It is designed to fly at MD, but at MD we end up in an undesirable condition. This is called unstarted inlet, because this is a big shock wave standing there in front of the inlet. Because of this position, we are losing a lot of mass from this one. Now all these things what I'm explaining is all happening over a very small fraction of time frame. I'm taking a snapshot of the events that is happening here. So the shock wave must be swallowed up quickly. That is what we call as the starting of the inlet. That swallowing up process is called the starting of the inlet. There are three methods that are followed to start up the inlet. One is overspeeding, other one is self-starting or Controvich-Donaldson type of inlet, or variable area. Adjust the throat area, then you start the shock. But before that, we need to understand, when I say we need to swallow the shock, basically what I'm saying here is we have to quickly move the shock from here to bring it here. So we need to understand the physics of the problem, physics of what is happening when the shock is somewhere here. And how can we stabilize the shock? So this is the thing which we'll first look at it, then we'll look at the methods of starting the inlets. So this is what I have already discussed here. The three methods to start: overspeeding. We will first look at the stability mechanism, then go into this one here. Okay. Now before we go into the stability of shocks, now we need to get this understanding right. Now this is the pressure at 1, P1. Now this is the shock. Let's say this is a strong shock. When there is a strong shock, it jumps to pressure P2. The temperature increases, and here is the total pressure. Now let me consider that there is a weak shock. Weak shock means the phenomena is the same. Whenever the shock, the flow jumps. But because it is weak, the pressure is, static pressure increases less. And the total temperature. So let's call this 1A. Shall we call this to avoid this confusion? This is 1, this is 2. 1 to 1A, yeah, just to say, or we can call it 3 also. Now here is this PT at 1A. So here is PT1, PT1A, PT2. Now I want to look at it from, this is the shock. Now the green one is weak shock, strong red one is a strong shock. Now I want you to picturize it on a relative basis. There are two shocks forming there. One is weak and other one is strong. On an absolute scale, absolute basis, whenever there's a shock, the total pressure decreases. That is absolute. Okay. On a relative basis, if it's a weaker shock, the total pressure is greater than the stronger. Are you able to picture this one here? This total pressure PT1A is greater than PT2 on a relative basis, and this is a weak shock. This is strong shock. On an absolute basis, everything, whether it's a PTA or PT2, it should be less than PT1 on an absolute basis. But on a relative basis, we can see that if it's a weaker shock, the total pressure is relatively higher than this one. Okay, we need to have this understanding in mind. And now let's go to this one, stability of shocks. Now let's look at the convergent geometry. Now there are two things we need to look at. One, because of the geometry itself. When a supersonic flow enters into a convergent geometry, what will happen? The Mach number decreases. Yeah. So now let me bring this up here. The Mach number here is less than the Mach number which was here. This is due to the geometry itself. When the Mach number decreases, the intensity of the shock also reduces. When you have high speed, high Mach number, the intensity goes up. Okay. Now here you can see that the intensity is reduced since this is the reduction in the Mach number. Because of the reduction in the intensity of the shock, the total pressure downstream increases in line with what we discussed in the previous slide on a relative basis. Understood, all of you? Yeah? So when this total pressure downstream of the shock, we are talking about what is happening in the convergent part of it. The total pressure downstream of the shock increases. Now we already seen that the mass flow rate per unit area is proportional to Pt square root of gamma by RTT. We looked at all these equations here. 1 plus gamma minus 1 by 2 m square, all these things. Let's not worry about it. Let's look at it like this. The mass flow rate is directly proportional to total pressure. Now, after the shock, the total pressure increases. So here is the shock. There is the mass flow rate downstream of the shock is very strong. It is creating a strong suction effect. It is pulling the shock. Because of the higher total pressure, it is directly proportional to the mass flow, which is drawing the shock closer to the throat. Strong suction effect. Now, let's look at it. We're taking a snapshot again now. Let's look at what's happening here. We are moving to section 2 there. When we move there, again due to geometry, the Mach number decreases. Okay? Well, I think this is what I explained here. Now, if we again move it to the section 2, because of the geometry, the Mach number decreases, the intensity of shock decreases even further, the total pressure downstream of shock increases even much higher on a relative basis. It creates even stronger suction flow, which quickly draws the shock and moves it past through this. It quickly moves it past through somewhere here. So shocks are highly unstable in the convergent part. Okay. Now let's see what's happening in the divergent part. Now in the divergent geometry, because of the geometry, the supersonic flow Mach number increases. The Mach number of the flow increases. When the Mach number increases, the total pressure downstream, the intensity of shock increases, the total pressure downstream decreases. Now because of the decrease the total pressure downstream, the static pressure also increases up. So the static pressure downstream increases, and in a way it says that I'm trying to hold the shock here. I'm going to hold you up here. So you can have a better control of the shock by controlling the static pressure there. So shocks are stable in the divergent part of the nozzle, inlet, whatever it is, inlet or nozzle here. So increase in the static pressure will oppose the shock. So this is what you see here. So when you have an inlet, you have an unstarted inlet, we really wanted to make sure this shock, what you see here, is placed exactly at the throat. Why do we say that we want to place it exactly at the throat? Because this is the divergent geometry. Here we want this to be 1 so that this becomes subsonic. Then we can still have the benefit of increase in pressure. This direction. Maximum benefit of it. So for best inlet pressure recovery, we want to place it at the throat. But for practical reasons, we don't place it at the throat because any increase in back pressure will immediately cause the shock to be thrown out and it results in an undesirable condition. So shocks are always placed slightly downstream of the throat so that we can try to control the position of the shock by varying the back pressure. At the same time, we also put some shock traps which monitor the pressures before and after with the fast acting valves and then control it to keep the shock at the best inlet pressure recovery position. Okay. With this understanding, let's now quickly move on to the starting of the convergent divergent inlets. Starting is nothing but swallowing the shock. So here is the shock. How are we going to swallow it? One of the method is overspeeding. The other one is increasing area ratio, or these are called self-starting inlets, or it's also called Kontrowitz-Donaldson. Two people working on different places coming up with the same idea, Kontrowitz and Donaldson, coming up with the same idea. It's called Kontrowitz-Donaldson inlet, or sometimes KD profile. KD profile. So if this is the isentropic geometry, then KD profile will be something like this, which is having a larger area. It's a fixed geometry. For that geometry, for that design flight, this shock will just be placed at the lip. It's not at that point, unstarted point, which means that immediately it can be swallowed in and it can be started immediately. That is what is the increasing area. And the variable area throat is, you can vary the throat area, variable geometry. The reason why variable geometry is better, because you can get better inlet pressure recovery. This self-starting is good, but it has poor inlet pressure recovery because the Mach number of the throat will be higher. Okay, now this is just to give an overview of it. Now let's look at overspeeding. So we are starting from the rest. Okay, so there's no, it's about to take off. It has reached the unique subsonic solution, which is still subsonic flow. You understand this. Now we reached m equal to 1, hypothetical condition. Now tending to form the weak shock in front of the inlet. Are you able to follow? Yeah. And then when we try to go to low supersonic speeds, then weak shock will tend to form, and then closer to the design, it tends to become shock, a stronger shock, spillage takes place. Now, when you have the shock forming there, this equation, what we have discussed before, A by A star, was an isentropic solution, 1 by m and all these things, power gamma plus 1 by. But now a shock has formed. You need to account for the shock. Now you need to get the shock solution. So which means what I discussed before, A by A star, like this is an isentropic solution. But now you have a shock that is being formed, so we need to come up with a shock solution which looks something like this. So this is the expression for the shock solution. So here you can see that this is the isentropic, this one is isentropic, this one is the shock solution. So once you start from here, you travel all the way here, formation of the shock, you end up in the shock solution here. Now you're trying to overspeed it, basically increasing the flight speed, overspeed it and come to a point here. At the design point, it is still, at the design point, it is still unstarted condition. Okay, now you overspeed it, which means you're just about to start by overspeeding, but we haven't started yet. Now you see that this is the overspeed. Can you see that? You're starting from here, going all the way to design speed, unstarted inlet at this point. To start it, overspeed it. You increase the speed, bring the shock to the incipient lip position. Now then, once it is at the incipient lip position, the shocks are unstable in the convergent part. It will quickly get swallowed up. The shocks will quickly move in and then it will come up here. Then you will see that you will end up in a situation where you have a convergent divergent one. The shock is here. The flow all through is isentropic. isentropic. So you can see that you will be able to, let me see whether this is, once it has reached this, you place the shock at the incipient lip, then the shock is swallowed up here. The shock is here. Now the flow all through is isentropic. Can you see this path? So you start from here, go all the way here, and then you overspeed it. Thereafter, you go up here because you reach an isentropic solution. So you are now in the isentropic solution. So once the shock has been swallowed up, then you can decrease the speed of the aircraft, bring it back to the design operating condition. That's how you operate it with this inlets, and bring it at the best pressure, inlet pressure recovery. Okay, understood. So this is overspeeding method to start the inlet. And then, as I did already mentioned, the second approach is the Controvich-Donaldson inlet, where the convergent geometry is a unique contraction ratio that places the starting shock at the inlet lip at the design Mach number. These are also called self-starting inlets. They can start by itself because the profile, so I had already mentioned, this is the KD profile and this is the isentropic design profile. So when it is designed to have the KD profile, at the design condition flight, the shock will not stand there. Shock will stand at the. So these are the sequence of events that happens in a Controvich-Donaldson inlet. At the design condition, this is the most important thing. Normally, under isentropic design conditions, the shock will stay here. MD, the shock will stay here. But now here you can see the difference here. At the design conditions, it will be placed at the incipient lip position. And then immediately by itself it will start because it's highly unstable in the convergent part. And then the shock will be swallowed and then you can have this. The main drawback of this self-starting inlet is a high inlet pressure recovery. Now, combination of both is the varying geometry. So you enlarge varying geometry, increase the area, swallow the shock, and bring it to isentropic operation. But there are other challenges, additional weight to the inlet, and so on. Open throat opening and throat Mach number are similar to Controvich one. After swallowing the shock, the inlet throat can be brought back to the original geometry. They have high pressure recovery, high performance, but then it comes at the extensive cost of the mechanisms and sensors to move it back to the isentropic position. Okay, so now we have learned about convergent divergent inlet, sequence of events that takes place from the start, challenges that we face, and the unique subsonic solutions leading to the formation of the shock that is formed outside the inlet at the design condition, that is called the unstarted inlet. Now we also looked at the way how to stabilize the shock, and we learned that the shocks are highly unstable in the convergent part, they are stable in the divergent part. So we looked at the ways to start. One is overspeeding, then other one is self-starting using a different profile, also called Controvich-Donaldson profile, KD profile. These are self-starting inlets, but they have drawbacks. They can start, but they have poor inlet pressure recovery. The way to resolve it is to go for varying area, which is good, but the additional cost comes with the weight and mechanisms involved in it. So you open the throat, swallow the shock, and bring it back to isentropic conditions. Now we're going to look at a normal shock inlet. 10 minutes, something. normal shock inlets. The main advantage of normal shock inlet is this is what I mentioned, the normal shock inlet here. It needs to have a sharp lip, because you can see that even a subsonic diffuser could be used for, a subsonic diffuser is used for supersonic applications. If you look at the commercial applications here, commercial aircrafts, you can see that this is the so here this is the blunt nose of it, but the only difference here is that you make it sharp. Okay, so that is the difference what you see here. But here the geometry is of diffuser geometry, here also of the diffuser geometry. So this is designed for m less than 1. The same diffuser geometry can also be used for supersonic applications, but by making the spike a bit sharp, because after shock flow becomes subsonic. So what are the advantages of this kind of inlets? They are very short length inlets, because you can operate up to Mach number 1.6. So they are Mach 1.6, because we will see that the inlet pressure recovery is up to 90% with Mach 1.6. So you can still have very good inlet pressure recovery with normal shock inlets. The short inlet length, weight is less, no movable parts, low supersonic applications, so ideal inlet for missiles. If you want to have missiles to be fired with low cost, fixed geometry, reduced length, and then normal shock inlets are ideal ones. So this is what you see here. So here it is supersonic. You can hold the shock at the lip, inlet lip. The capture ratio is 1, no spillage. And this is what you call as a cowl. So immediately when it becomes subsonic, it becomes like a subsonic inlet. The flow entering in, the pressure increases and the velocity decreases. We have no starting problem because there is no throat. We will have starting problem only when there is a throat. Throat is occurring at the middle, but the throat here is the inlet itself is a throat. Okay, so we don't have a throat, so there's no starting problems. Now, normal shock, the position defines whether it is effective in its operation or not. What are the challenges faced? I've shown the 3 positions here. So this is the design mode of operation, which is called the critical mode, where there is no spillage. If the back pressure can increase or decrease in the operation phase. If the back pressure increases, the shock is thrown out. When the shock is thrown out, you end up in spillage. And this is called subcritical mode of operation. When the back pressure decreases, then the shock is drawn into the inlet itself. Now, when the shock is drawn into the inlet, now you should not forget that there is a boundary layer here. This shock will be placed on the boundary layer. There will be shock boundary layer interactions there. And this will separate the boundary layer and will create some distorted flow getting into the inlet, which can damage the compressors if it is a normal turbo machinery applications and so on. Now then when we go up, the Mach number decreases, then you have poor inlet pressure recovery. So when you have the supercritical mode, you have poor inlet pressure recovery. Okay, now the performance of this is drawn through this here. On the y-axis, if you have this pi d, which is the inlet pressure recovery. On the x-axis, if you have this mass loss. Now approximately up to 80%, you can say it's a bit of a stable region, 90 to 95%. 90 to 80, between 80 and 90%, you can say is stable regime here. So under subcritical mode, you don't lose, your pressure recovery is not bad, but you lose mass. Under supercritical mode, the pressure recovery is low, but you will not lose much of the mass. So this is the critical mode of operation. Is that clear for all of you? So this is the performance map of these normal shock inlets. Now, as I did mention, these normal shocks are ideal up to Mach 1.6 because the inlet pressure recovery under the design mode is up to 0.9 here. So this is the chart, normal shock, total pressure recovery as a function of Mach number. So here you can see at Mach 1.6 here, you have good inlet pressure recovery. So with the normal shock inlets, you can go up to Mach 1.6, normal shock inlets. But man's quest for speed has never stopped, wants to go for higher speeds. When you go for higher speeds, this is not the solution, because you can see that the inlet pressure recovery immediately reduces here. The total pressure recovery normal shock rapidly deteriorates beyond Mach 1.6. So we have to look for external compression inlets. So as I did mention this morning, supersonic flow deceleration is more efficient using multiple shocks configuration than normal shock. When you use multiple shock, this is how the graph will shift. This is how the graph will shift. More number of shocks. Okay, so this is what will, this leads to development of external compression inlets. So we stopped with the normal shock inlet, and we found out that if we want to go for higher Mach numbers, then probably it's better to decelerate over more number of shocks and to also go for external compression inlets. And we discussed this in the morning, so it is much easier for us, this remaining section. And so the throat is at the cowl lip. So this is the cowl, and this is the cowl lip. So here is the minimum area. So this is the throat. This is an external compression inlet because the compression takes place outside. And you have this compression ramp. This is a single compression ramp. You have one oblique shock placed in the external compression ramp. And there are a lot of things with the position of the shock also. There's a lot of things going on here. Here the oblique shock is placed exactly on the cowl lip, and the normal shock is placed at the throat. This is a single compression ramp. Now here in a double compression ramp, here you have an oblique shock, one from the leading edge, and then the second oblique shock from the second part of the compression ramp, and they're all placed on the cowl lip and with a normal shock at the throat. Now what you see here is a cowl shock. Because the shocks are all placed on the cowl lip, the flow coming in here will result in the formation of a shock. This shock is called the cowl shock. This is not a very desirable one because it can create a lot of drag effects affecting the external aerodynamics of the vehicle, which we'll be looking at it shortly. And here you have this triple compression ramp. This is the inlet with a two-dimensional. This is the inlet, entry, mouth. So here is the external compression ramp, one, oblique shock 1, and then it's oblique shock 2, oblique shock 3. And now you can see that when you go for higher and higher speeds, higher and higher Mach number, you're forced to decelerate the flow with multiple shock trains. At the same time, what you can observe is that you turn the flow. Every time you add an oblique shock, you turn the flow. So the flow will turn excessively. So there is a limit up to which you can also operate on external compression round, because the cowl lip, then eventually you end up in turning the cowl lip in such a way that you end up in a situation where theta will go greater than theta max. There will not be any oblique shock solution, what we saw this morning. So there is a limit up to which you can turn the flow. If you want to go for higher Mach numbers, then you cannot use the external compression ramp. Maybe up to 2.5 is the best one with the external compression ramps. So the reason why we go for multiple shock is to go for inlet pressure recovery. Say for example, if you're going for Mach 2 or 2.5, if it's a normal shock, you see it's a very poor inlet pressure recovery. If you go for two shock train configuration, one oblique shock and one normal shock, you are immediately able to improve the recovery. If you go for 3, you are still getting better, and go for 4. So it's always better to decelerate over multiple shock trains. But then, as I did mention, there is a limitation for external compression inlet, because you are turning the flow excessively to decelerate it. Then your cowl lip angle also turns to accommodate the flow to get into the engine. But if it turns, if it comes to a situation where theta is greater than theta max, then you will not have oblique shock solution. Yeah, now let's look at the challenges of it. Shock locations and their effect. The engine performance is affected if there are enormous mass and pressure loss. Inlet pressure recovery is affected by the shock system. Now, the shock system, it defines the internal performance. Internal performance is the inlet pressure recovery, and external performance is to the external drag grasped by the inlet. So, for example, with this shock will have a higher static pressure here. This will affect the external aerodynamic performance of this engine. But then if you have a reduced mass loss, then you have a better internal performance here. So you need to outweigh the internal and external performance. Now we're going to look at the situations where oblique shock is placed onto or slightly below the cowl lip. That's what we're going to look at. And the terminal shock exactly on the throat. Now here you can see that this oblique shock is placed on the cowl lip and normal shock placed at the throat, which means the capture ratio is 1 and no spillage drag. So you have a good internal performance. You're not losing any mass of air, and you have good inlet pressure recovery, but you have a strong cowl shock, which leads to wave drag, and it deteriorates the external performance. So you have a good internal performance, but your external performance is affected due to the position of the oblique shock. Now, if you look at the second situation here, the oblique shock is not placed on the cowl lip. It is placed slightly down to that of the cowl lip, slightly downstream of the cowl lip, and the normal shock placed at the throat. Now, because we have placed a little bit down, you are turning the flow. So here it is M1 and M2. Now M2 is less than M1, which means the intensity of Mach number is reduced. Then the intensity of cowl shock will also reduce. Is that clear? Compared to this situation, here entirety of M1 will have an effect on this one. It's a much stronger shock, but here it's a weaker shock. The oblique shock is projected below the cowl lip, creating some supersonic spillage. Of course, there are some mass loss here, but cowl shock is now weaker, causing lower external drag. But the capture ratio is less than 1, and so there is a spillage. A weak cowl shock leads to lower wave drag penalty of the inlet. Now, there are lots of other challenges related to the position of the normal shock. Now, when the normal shock is placed at the throat, then it is the critical mode of operation. If for some reason, if the back pressure increases, then the shock is thrown out. It is at this point. That is subcritical mode of operation. And if the back pressure decreases, the shock is drawn into, and this is called the supercritical mode of operation. In real applications, this can happen, moving of the shock waves in engine flights. This moving of the normal shock to the subcritical to supercritical to subcritical to critical is sort of an instability, and that instability is called the bus instability. Okay. For normal shock should be placed at the throat for best pressure recovery, but in reality, we will end up in a situation either it can be subcritical or critical or supercritical modes of operation. Now let's look at the supercritical mode. Now, always, as I did mention, there is a boundary layer. The boundary layer distortion will take place, the boundary layer separation, and the boundary layer a distorted flow will enter into the engine, which is a desirable phenomenon. So under supercritical mode, low total pressure recovery, and the shock intensity also increases because of the geometry diverging one. The Mach number is stronger in the normal shock than at the throat. This will have the shock boundary layer interactions, and you have a distorted flow entering into the engine. One of the ways to deal with is the boundary layer suction techniques, which could be done to solve this problem here. Subcritical mode is what you see here. When the back pressure increases, the normal shock is pushed out of the inlet lip, and now the shock is on the external compression ramp. Now there are two challenges here. Now there is also a boundary layer effect here. There will be boundary layer separation, shock boundary layer interactions, and the distorted flow coming into the engine, and also partially blocking the entrance into the engine. Now, because of this, the spillage drag also increases. Also, because this is normal shock is now on the compression ramp, but also it affects the flow here, and so you result in formation of the vertex structures of the flow that is encountering the normal shock. The intersection of shock outside the inlet creates vertex shear layer distortions. This is what it is, what you have. The normal shock on the ramp separates the boundary layer, and this is called oscillations, large amplitude oscillated flow pulsations, which distorts the flow into the engine. This oscillated flow is called the bus instability. So this bus instability is just a cyclic movement of the normal shock at the critical mode, and then the back pressure increases, it is thrown out. The normal shock sits in the compression ramp. When it is on the compression ramp, on the ramp side, it has a shock boundary layer interactions. The boundary layer flow separates, and it causes a distorted flow coming into the engine. Then the actual area through which the flow is decreasing, the strong flow is drawn in, that causes the shock to be drawn to the critical mode of operation. Then it is in the critical mode of operation. Then the back pressure increases, the shock is thrown out. Then you have the same phenomena happening. So this moving from subcritical to critical and critical to subcritical, this is what is called this bus instability. Again, like what we did for the normal shock inlets, we can draw the performance. So this is the critical mode of operation. This is the critical mode. Best design mode. Place the oblique shock on the cowl lip and normal shock at the inlet, cowl inlet lip. This is the design point operation. But in reality, you can end up in a subcritical mode where the back pressure increases, the shock is thrown out. Now, when this happens, you're losing mass, spillage. So this is what you see here. You are losing some mass. You can see that there is a limit. Up to 80% of the mass is a stability margin. Okay, beyond which then you affect the performance of the engine significantly. Now, the other phenomena is if you have the supercritical mode, then you're not going to lose much of the mass, but the pressure recovery, inlet pressure recovery reduces here. Now, what we have done so far is the fixed geometry external compression ramp. The development is to have an external compression ramp with the ramps which could be withdrawn or projected. These are variable geometry ones. The mass flow demands are different for different Mach numbers. When we have a fixed external compression ramp of variable geometry, the leading ramp is always fixed, solid wedge. It is normally of 3 to 5 degrees. The trailing ramps may extend into the flow or withdrawn from the flow with the hydraulic actuators. Of course, this adds weight and the mechanisms on it. So under low speed conditions, subsonic conditions, you really don't need to have this ramp projected into the flow. But when you get into the higher Mach numbers, to keep the boundary layer controls, you can use this variable in the geometry of controlling the flow entering into the engine. The withdrawal position, collapse ramp position, large inlet area during takeoff, climb, subsonic cruise and transonic accelerations, extended into flow during the supersonic conditions. The inlets will be able to adjust itself to provide different mass flow rate to the engine at different flight speeds and altitudes. Now, using this variable geometry, by controlling the position of the ramps, you can control the bus instability, or it can be eliminated by these control mechanisms to have an undistorted flow or minimize the distortions to the flow that enters into the engine. It also has its own limitations. As I did mention, they can fly up to Mach 2.5 external compression inlets, because in order to decelerate the flow, you need to have multiple compression ramps. We have seen that single compression ramp, dual compression ramp, triple compression ramp. The more number of shock trains are required, it is more efficient to decelerate, but then at the same time, the flow has to turn from here to here to here. Then the cowl lip position has to also turn. So the angle should be less than theta max. Otherwise, the shock will be thrown out as there's no oblique shock solution, then it ends up in a bow shock. The penalty comes from excessive cowl drag. Cowl lip has almost the same inclination with respect to flow as that of the last compression ramp of the inlet. This is exactly what I did mention. It's almost turned such that the last compression ramp and this is almost in line with it. So there is no oblique shock to hold on to. Large flow deceleration needs a larger supersonic flow turning. Hence, cowl lip angle may exceed theta max of the oblique shock, resulting in a bow shock. Now, what is the solution for this? Instead of having a stronger cowl lip, make the cowl lip to be in line with the flow. Don't turn it too further. This is what happens at m equal to 2.5. If you go further, then you have to turn even beyond, then it becomes theta greater than theta max. That's not going to happen. So to overcome this, keep the cowl lip to be in line with the flow, so that the compression ramp, the last compression ramp, will have an oblique shock, will come and hit the cowl lip, and then it has a reflection inside the inlet. So now you can see that the development is going from the external compression to mixed compression, where you compress not only external but also internal to the reflected oblique shocks here. So that is what is called the mixed compression inlets here. So here you see, this is the compression. What I'm drawing here is the compression ramp. The first oblique shock, 1, and then the oblique shock 2, the oblique shock. Now you can see the cowl lip is no longer inclined, it is in line to the flow. So that the shock coming from this last ramp will be reflected into the inlet. So it's a reflected oblique shock here. Then again you have another reflection here, then you have this normal shock here at the throat. So here is the mixed compression, not only external compression, that's what we were looking at, also internal compression. Now you see that we end up in a convergent divergent inlet. When you end up in a convergent divergent inlet, then you see this normal shock. So we have to face the problem of unstarted inlet. Whenever we have this convergent divergent inlet, this unstarted inlet conditions will come. So we need to look at the mechanisms of starting the shocks to swallow the shock quickly so that it comes here. Now this is the kind of inlet that's being used in Concorde, but there are lots of control mechanisms. What you see here, there are bleeds here, shock traps, and fast acting valves to quickly control the flow. Now with this mixed compression inlets, the benefits is that we can operate at higher Mach numbers, Mach 4 to Mach 5. The multiple ramps both outside and inside results in high pressure recovery. The benefit is you decelerate over more number of oblique shocks, very less or no penalty of the cowl wave drag, because the cowl is almost inclined to the flow. What are the challenges? It has an internal throat. I did mention, when we have an internal throat, we end up in having a starting problem. The external surface ramp, bus instability is also one of the issues. The reflection of shock on the internal surface, shock boundary layer interactions, distorted flow to the engine. The other thing is a sharp cowl lip, sensitivity to misaligned force. So for example, at takeoff, the angle of attack will be different. And to deal with this, there are control mechanisms, what is called the cowl lip articulation. You can control the position of the cowl lip according to the different angle of attack to minimize the drag, particularly during the takeoff, climb, and side wind. So what I've done here is that I post the challenges here and the solutions here. You have a starting problem that can be solved using a variable throat, variable compression ramp. You have a problem with the external bus instability in unstart mode, boundary layer separations. Now bus instability, boundary layer section, and all these things could be controlled with the boundary layer section and throat bleed. So you can have the suction, boundary layer suction techniques employed into it. A reflection of shock on the internal surface, shock boundary layer interactions, distorted flow to the engine is a problem. Now again, boundary layer section and porous materials could be used in this mixed compression inlets. Unstart problems could be handled by having a normal shock traps. These are shock traps, which is basically two fast acting valves detecting the pressures before and after all the time. If there is a high back pressure, if it thinks that the shock is going to move, immediately one of the valves opens and reduce the back pressure to keep the shock in that position. Sharp cowl lip, sensitivity to misaligned flow. movable lip and boundary layer control techniques. These are the strategies which can be used to deal with this, which is basically cowl lip articulation. Okay. Finally, this is almost the last slide on this one. Performance of mixed compression inlets. So here's the design point, and here is the stability margin as we have done before. Whatever things what we have seen, you can have the subcritical and supercritical mode because of the shock waves coming into the compression ramp. The flow angularity during takeoff is a sensitive issue for sharp cowl lift configuration of mixed compression inlets. That is done by cowl lip articulation, which is the articulating cowl, which is movable lip, not just a fixed solid wedge there. It's a one which the wedge is fixed, but the mechanisms to control it. Spike bleed and bound layer control techniques overcome the poor low speed characteristics of mixes. So basically it's a fully controllable with a lot of several mechanisms to accommodate to have better aerodynamic control of the flow into the inlet. Supersonic flow requires a design of a sharp leading edge of the cowl, wings, and other components, but they are not desirable at slow speeds. Because at slow speeds, there is subsonic flow. There are no shocks there. So sharp corners and subsonic is not a desirable phenomenon, which cause excessive flow separation in these things. So these are some of the challenges when you operating the supersonic flight to go all the way from rest to supersonic condition. But these are happening over a shorter time period of time because majority of the time it will be flying at the design supersonic speeds. Okay, so finally, just to summarize, so we looked at it as a normal shock which can be operated at Mach 1.6, and then external compression can go up to Mach 2.5, and then mixed compression can go up to Mach 5 and so on. Okay, so that's what the theory I want to cover with this application of shock waves in supersonic inlets. What we can do is we'll try and work out a bit more problems so we'll be able to understand this better. So problem number 7 is the latest strategy what we have looked at. So it is a mixed compression inlet. So this is the problem about mixed compression inlets. The inlets of the most advanced fighter aircrafts are designed with two-dimensional wedge-type diffuser. These inlets use a combination of external and internal compression system, as shown in figure below, to decelerate the flow using 3 shock systems, 2 oblique shock and a normal shock to bring the flow to subsonic condition. If the flight Mach number is 3, then calculate the following. Calculate the overall total pressure ratio. Calculate the overall static pressure ratio. The overall total pressure ratio if there was only one normal shock. Okay. So here is the inlet configuration. Here is an oblique shock. So here is the oblique shock 1. So M1 equal to 3. The flow that encounters the oblique shock will turn exactly by the angle of this recompression ramp that is given as 15 degrees. So the flow turns. If there is no intervention, the flow will come and hit the internal surface of the cowl. To avoid that, now the cowl lip has been straightened so that we could operate this at higher Mach numbers greater than 2.5. So you have a reflected oblique shock so that the flow will not hit the internal wall. So here it is M1, here it is M2. The flow has turned by 15 degrees. Now, because of this reflection, what we have seen this morning, instead of going in the same direction, the flow will turn exactly by the same amount. It has turned, and now it goes parallel to the surface, and then it encounters the normal shock. So this is M3, and then it is M4. So this is 1, 2, 3, 4. Question number 1. What's the overall pressure ratio? What is PT4 by PT1 for the overall system? That will be PT4 by PT3 for the normal shock, and then it will be PT3 by PT2 for the oblique shock that is reflected into PT2 by PT1. This is for the oblique shock 1. So that is the question number 1. What is the overall static pressure ratio? What is P4 by P1? It is again P4 by P3 that is happening over the normal shock, P3 by P2 happening over the oblique shock that is reflected, and then P2 by P1 due to the oblique shock 1. That's one here. The third part, this is A, this is B. The third part is, what's the overall total pressure ratio if there was only one normal shock? What they're saying here is that you don't have the shock train, you just assume that it was only a normal shock, and if a Mach number of M1 equal to 3 encounters a normal shock, what will be the pressure recovery? So this is 1 and 2. What will be PT2 by PT1? Total pressure recovery. Also, we can, for sake of interest, we can find what is P2 by P1 if there's only one normal shock. Okay. So let's look at it. Oblique shock 1. You have M1 equal to 3 and theta 1 is equal to 15. With this, you can find the value beta 1. What's the value for beta 1 you have? 30? 32 degrees. You have this oblique shock, wave angle. M1n is equal to M1 sine beta. Anybody calculate the value for M1n? 1.59. For this M1 1.59, what is PT2 by PT1? 0.8986. 89. Also, you can find out what's the value for P2 by P1. 2.783. So now we have to find out what is M2N. We need M2N to find out M2 sine M beta 1 theta. So what's the value for M2N? 0. 0 point?
2.3.
No, M2N.
M2N 0.67.
0.6715. M2
2.3.
2.3. So which means you can see that the flow has decelerated from 3 to 2.3. So now we are entering into oblique shock, that is reflected, or oblique shock 2. Oblique shock 2. So we have M2 equal to 2.3, and the theta is the same angle through which the flow is turned back. Yeah, turned back. So what is the oblique shock wave angle? Beta 2. How much? 38.5 degrees. So from this we can find
The cowl angle is 5 degrees.
oh yeah, the cowl. Okay, I didn't yeah, this angle is given as 5 degrees, so we need to account for this, otherwise the flow will hit the internal cowl surface. So the flow has to turn by additional 5 degrees, 15 plus 5. So the value for 38.5 is not right one, yeah? Not always that will be the case, but here it is 5 degrees is given here. Is 46 degrees, yeah? So M2N is equal to M2 sine beta 2 What is the value for M2N? 1.65. For 1.65, what is the total pressure ratio?
0.876.
0?
0.876.
0.876. And for this one, the static pressure? 3.01. 3.01, yeah. What is the value for M3N? 0.65, 0.654. Yeah, is that what you're getting? Okay. So from this you can find M3 it should be less than 2.3. What is it? 1.492. So now you can see that we have decelerated the flow from 3 to 2.3, and then now it is 1.492. So now you can see that we are bringing the Mach number to, now it is going to encounter the normal shock. It is less than 1.6. We know up to 1.6 it is 90%. So it's going to be have a better pressure recovery. So it should be 0.9 something, isn't it? So from this, what is PT4 by PT3? PT4 by PT3, and then what is P4 by P3? 0.9, 0.9329. P4 by P3, 2.42. So you can now calculate the inlet pressure recovery. PT4 by PT1 is equal to PT4 by PT3 for the normal shock, PT3 by PT2 for oblique shock that is reflected, and PT2 by PT1 for the oblique shock 1. 0. Hmm? 0.7, 0.7379, yeah? 0.7359, okay, 0.736. So you are able to get a recovery of 0.73. You'll be able to appreciate this only when you find out what is the what is the Mach number of the flight. It is 3. For M1 equal to 3, what is PT 2 by PT1. Just a normal shock for M. Huh? For M equal to 3. 0.3253. So now you can see the benefit of decelerating the flow over multiple shock trains. Okay. I think there is one more parameter that we were asked to calculate, which is P4 by P1. What is the pressure amplification? It is 20.5. So let's see. So now you get the feel about how to deal with supersonic inlets. Yeah. So there is one more problem for today. The last problem is problem number 8. We'll finish for this day, and then we'll finish this problem, and then we'll finish for this day. Problem number 8. A two-dimensional wedge-type diffuser was designed to operate in supersonic flights that would fly at Mach M1 is equal to 3.5. The inlet was designed to house two external compression oblique shocks. So here is the oblique shock 1. Here is the oblique shock 2. Designed to house two external compression oblique shocks, a normal shock and a subsonic diffuser. So here is the cowl lip, and here is the normal shock, which is the minimum area, normal shock, and then the diffuser. So this is 1, 2, 3, 4, and the subsonic diffuser, this is what it is, subsonic diffuser. So it's a diverging part here. So which means somewhere here the engine is later on the combustor, whatever it is, 5. Assume that the total pressure loss in the subsonic part of the diffuser accounts for, well, the value is given here, PT5 by PT4 is given as 0.95, isn't it? So the loss is accounted as 4%, 4.5% is the loss. So we are able to recover 0.955 is the pressure one. And calculate the total inlet pressure recovery for this inlet. So we are asked to find out what is PT5 by PT1, which is PT5 by PT4. This is for the subsonic diffuser. Then we have PT4 by PT3 for the normal shock inlet, and PT3 by PT2 for the oblique shock 2, and PT2 by PT1 for oblique shock 1. So this is what you have to find out. So we start with oblique shock 1. M1 is 3.5. Now the floor turning angle is given in the problem as 10. Theta 1 is equal to 10. From this, find beta 1. M1n is equal to M1 sine beta 1. What's the value for beta 1? Twenty-four, 24.5. So that is beta 1. So what is M1n? M1n is equal to 1.45. So for this M1n, what is PT2 by PT1? Zero point 0.9448. So once you got M1n, what is the value for M2n from the tables? 0. M2n is 0.7196. For M2n, that value is equal to M2 sine beta 1 minus theta 1. So we can find M2 is equal to M2n by sine beta 1 minus theta 1. What's the value? Somebody said 2. 2.87. 87. So we're going for the oblique shock 2. M2 is 2.87 and theta 2 value is given. What is beta 2? How much? What's the value for theta 2? Theta 2. The flow has already turned by an angle 10. So with respect to 10, it again has to turn only 10 degrees. It is given as 20, so the actual flow turning is 10. So what's the value for beta 2? 30, 32 degrees. Is that what others are getting? 29. 29, yeah? So 29, and then we have M2n is equal to M2 sine beta 2. What's the value for M2n? 1.39. PT3 by PT2. 0.9607. What is M3N? 0.744. And M3 is 2.285. Now this 2.M3, it's not really a good value. You can see that the flow is M1, the flow turns, it's not optimized, the data is not optimized here. So this is 10, this is 20. In other words, this is 10. M2, M3. Ideally, we want M3 to be less than 1.6 to have a good pressure recovery. Now, if you have this high value of M3, 2.2, you will see that it will have a very poor pressure recovery. So even though you have 0.9, 0.9, if you multiply this, you will have very poor pressure recovery. So for this M3, what is PT4 by PT3? Or PT4 by PT3? 0.58776. 0.587. Yeah, 77. Okay, 0.587. And what is M4? M4 is not asked. What M4 is not asked. What is the value for M4? 0.583. Hmm? 0.5356. So let's calculate what is the total pressure recovery. It is PT5 by PT1. PT5 by PT4. This is in the subsonic diffuser. PT4 by PT3 in the normal shock. PT3 by PT2 for the oblique shock 2. PT2 by PT1 for the oblique shock 1. 0.51. Nearly 50% is lost. Yeah. So obviously, when probably it would have been better if we had, because this is fully an external compression inlet, so we see the defects there. So we're trying to deset only with the 2 oblique shocks and 1 normal shock at Mach 3.5. Ideally, we could have gone for 1 more, then cowl lip would have turned, or the best way is to decelerate with mixed compression inlets to have more oblique shocks. So we can improve this 0.51. Okay, so I think you could have got some hold about supersonic inlets now. Yeah. So I think with this, I would like to finish today's lecture. So just to summarize, today we looked at started this morning quite fresh with shocks. Started with a normal shock, and then we tried to solve a problem for normal shock, and we discussed about the shock shock wave tables, and then we moved on to oblique shock theory, and we discussed how this oblique shock could be used by resolving the flow normal to the shock to use this normal shock tables. And then from that time onwards, we are trying to solve some problems. And then later, in the afternoon, we were looking at application of shock waves in this one. So we looked at how we could design the supersonic inlet. Even though it's designed to operate at supersonic speed, it causes problems even at a unique subsonic speed, because it also has a subsonic solution at which this throat starts to choke. This starts building up the pressure waves, results in the formation of an shock wave, and resulted in the unstarted inlet. So, and then from that point, we learned how the shocks could be stabilized in the divergent part, because it is highly unstable in the convergent part, and then how we can vary the back pressure. From that, we looked at different starting methods. One is the overspeeding method. Other one is a self-starting, which is nothing but having a unique profile, KD profile or Kontrabich Donaldson profile, where we can keep the unstarted shock at the inlet lip. So once you bring it to the inlet lip, we can know for sure it is unstable in the convergent part. It will quickly move through and get stabilized in the divergent part. The other technique is to go for a variable area, adjust the area, open it up, swallow the shock, and then bring it up. Otherwise, you will have poor pressure recovery. So these are 3 starting methods. From there, we went on to look at the normal shock inlets, which is very effective, very efficient, less weight, reduced length, fixed geometry, ideal for Mach 1.6, very useful for missile applications. And then if you want to go for higher Mach numbers, normal shock is not the suitable one. Normal shock must have a sharp cowl lip to hold this one. Blunt will be an unstarted one. So if you want to go beyond Mach 1.6, then you need to have an external compression inlet. External compression inlet, so you can have a single external compression ramp or a double external compression ramp or a triple external compression ramp. And then there is a limitation up to which you can compress it. A limitation in the Mach number up to which you can compress it. So if you go higher and higher the Mach number, then the cowl lip has to turn. It will end up in a situation, the last ramp will almost be in line with the cowl lip. In that case, where theta will be greater than theta max, then you will not have an oblique shock solution. Then in that case, we end up in forming a bow shock, which is not a desirable phenomenon. So if you want to go for beyond Mach 2.5, the solution is to change the cowl lip to be in line to the flow, and to make sure the last compression ramp to have an oblique shock that hit the cowl lip, and to have a reflected oblique shock which happens inside the inlet. So it becomes a mixed compression inlet, and then another reflection. Then you have the normal shock at the throat. So then that comes to the mixed compression inlet. It's the most sophisticated inlet. We can go up to Mach 5 and so on. And the problem is, it is a convergent divergent geometry, which will have all the problems what we discussed, but all the problems could be resolved with extensive control mechanisms of boundary layer suction and porous materials and shock traps and cowl lip articulation. All of these techniques could be used to control the shocks. And then Based on that, we try to solve problems on both external compression and mixed compression inlets. So with this, I could say that we have completed today's lecture on shock waves. Tomorrow morning, I will look at the shock interactions, reflections, like reflections and unlike reflections, and touch a little bit on the Prandtl-Meyer expansion, and then we will look at the nozzles, and that will be the morning. And after that, that's going to be more interesting than this theory. We're going to have the more dynamic practical ones, Schlieren techniques, measurement methods, and the practical sections in the afternoon. I'm sure you'll be able to make use of the theory, what we understood, to see it in real and then enjoy it. Okay, see you tomorrow then, yeah? When we come to that, I will be covering that. So you will have a terminal shock only for ramjet applications. Yeah, so that will be overcome by eliminating the terminal shock. We will discuss it when we do. That will be on Friday, last day. Yeah.